Hi, the seventh lecture of this course will be about logic. Its main purpose is to introduce you to some of the basic concepts and notations of mathematical logic so you can read, understand, and express yourself using its notation. At its core, logic is about mechanizing the management of what to believe. That is, what to consider true, at least in the context of mathematics and similar disciplines. Generally, belief management is an important and complicated process that involves determining the facts of a situation, which are often imperfect or uncertain, which cannot always be independently verified, and then drawing the right conclusions from them. Logic tries to realize some of that kind of reasoning process, at least in the context of mathematics, as rule-based manipulations of strings. The strings are expressions that represent statements about the truth or falsehood of propositions relating to mathematical objects. In principle, the rules describing the possible transformations on those expressions are entirely mechanizable, and so they can be implemented by computing machines. In order to discipline our reasoning in this manner, we need to represent truth and falsehood symbolically and unambiguously. We need a system of symbols so we can construct expressions about mathematical objects that are either true or false, and we need rules for manipulating those expressions. A key simplifying assumption is that we assume that any such statement can only ever be true or false. That is, the logic we shall be looking at assumes that only two truth values exist, which we shall represent as 1 for truth and 0 for falsehood. We start by looking at propositional logic. Propositional logic is concerned with how the truth of different atomic propositions connects and compares, and how to construct composite propositions from atomic ones. In this, an atomic proposition is a statement that is either true or false, like all propositions. It is atomic because for our purposes, we simply treat it as a variable symbol and do not concern ourselves with its inner structure. In particular, in propositional logic, we do not investigate whether an atomic proposition is true or false, but only how its truth is connected to that of other propositions. We do so by looking at the properties of logical operators, which we call connectives, because they connect propositions to form new propositions from them. The simplest logical connective is the negation, or the not operator. It is written as this hook-shaped symbol and set in front of the proposition it negates. We can describe what an operator does by building a so-called truth table. In this case, the negation only operates on a single proposition, so it doesn't really actually connect several of them. So we list all the possible logical values it can have, 1 and 0, and what the negation would look like in either case, here 0 and 1 respectively. Most other operators connect two propositions to form a new one. In that case, the truth table has 4 rows, 1 for each combination of truth values of the operands. The behavior of an operator can then be shown in a column in such a table, here for the operators logical and or, the implication for equivalence or if and only if, exclusive or, and the inversion of and, The AND operator is often referred to as conjunction, while the OR operator is called disjunction. With this, you could build a truth table for any expression using these operators. But how would you do the reverse, constructing an expression starting from a truth table? The simplest process goes something like this. First, you identify the rows in which the expression is true. Then you create an expression that is true for exactly this row and no others. To do this, you look at the values of the atomic propositions. In the first row, P, Q, and R are all 1 or true. The expression that is true only when they are all 1 and under no other circumstance is P and Q and R. So that's the expression for the first row. In the next row, the expression is true if P and R are 1, but Q is 0. Consequently, the expression that is true in this row only is P and not Q and R. Finally, in the last row where the original expression was true, P and Q are 0 and R is 1. So the row expression in this case is not P and not Q and R. So at this point we have three expressions that are each only true for one truth value assigned for P, Q, and R. The formula for the overall expression is the result of ORing these three expressions together. So that raises the question, are there any tables for which we could not find an expression with this method? And what does it mean for the three connectives and, or, and not? A table for an expression that is always false would not produce a meaningful expression using this method. However, there are simple formulae that are always false, so we could use one of those. What this means is that the connectives and, or, and not are universal in propositional logic. We can express any propositional statement, any formula with them. The connectives in our little table are not unrelated to each other. In fact, they often can be expressed in terms of each other. For example, try to write a logic formula that has the same truth table as the OR operator using only and not. And this is the result. Note what this means for the universality of operators. We had seen previously that using only and, or, and not, we could construct an expression for any truth table. And now we just expressed one of those, the OR operator, by using only the other two. Therefore, and not, conjunction and negation, are already universal. We don't even need the disjunction or the OR operator. This leads to the question, is there perhaps a single connective that could be used to express all others and that would therefore be universal all by itself? There is. For instance, the NAND operator can be used to express both negation and conjunction. Since these two together were universal, so is the NAND operator by itself. When discussing formulae or expressions in propositional logic, it is important to distinguish different parts of the language of logic. The first are elementary or atomic propositions. They represent statements that are either true or false, but in propositional logic, we won't, in a manner of speaking, look inside them or try to figure out whether they are true or false. Instead, we just represent them by placeholder symbols and assume they may be either true or false. The next are the formulae we construct from these elementary propositions and the various connectives we use to compose them. Using the truth tables for our basic connectives, we can build truth tables for any formula. Note, however, that the size of the truth table, specifically the number of rows, depends exponentially on the number of different elementary propositions in it. The truth table for not, with only one operand, had 2 to the 1 that is 2 lines. The one containing our various operators acting on 2 operands had 2 square 4 lines, and so on. Finally, we need some notation to discuss relationships between formulae, which is what we shall do next. First, however, we need some concepts to talk more precisely about how formulae are evaluated. Suppose we have a set E of symbols representing the elementary propositions of some formulae we are interested in. A function v that maps each of those elementary letters to either 1 or 0 is called an assignment. Note that in a truth table for that expression, the E would be just the symbols that we assign all combinations of 0s and 1s to, which allows us to then evaluate the expression. Any given assignment uniquely identifies a row in the truth table of an expression. Given an assignment of truth values to the elementary letters, evaluation assigns a truth value to every formula using only those letters. We can think of our set of logical formulae as being the closure of the set of elementary letters under a set of rules, similar to the expressions we built before using relations as generators. The precise rules used to construct our set of logic formulae depends on the operators we allow, but these could be the rules for and, or, and not. The valuation can then be seen as extending the truth table infinitely to the right, with one column for each well-formed formula. A particular valuation applies to one row, just as a particular assignment did before. And evaluation can be defined by recursion on the structure of the expression. In the following, we will use the same symbol V for valuations and assignments, whenever that distinction is clear from the context. With this, we can now discuss relationships between logic formulae based on their relationship of their valuations. For example, suppose you have a set of formulae A and a single formula beta. We say that A tautologically implies beta if and only if there's no valuation such that it is true for all A but false for beta. Tautological implication is represented by these turnstile symbols, and the reason it is called tautological is that it is true for all assignments of the elementary letters, that is for all valuations. Consider this example, which goes by the name modus ponens. The two formulae in A are P and P implies Q. Using the table, you can check that indeed there is no row, that is, there is no valuation, such that P and P implies Q would be true, but Q would be false. So those two formulae together tautologically imply Q. You can find a list of other tautological implications in the textbook. When two formulae tautologically imply each other, they're called tautologically equivalent, represented by the double turnstile symbol. The textbook also contains a list of tautological equivalences. Note that if two formulae are tautologically equivalent, it means they behave exactly the same way with respect to the values of the elementary letters in them. And so they can be substituted for each other. Consequently, this list of equivalences can also be used as practical rules when transforming and manipulating logical formulae. For example, the variations of De Morgan's rule can be extremely useful to move negations around or get rid of conjunctions or disjunctions. That's why it might make sense to keep a list of these around for references whenever you manipulate propositional formulae. A formula that is true for every assignment of its elementary letters is called a tautology. One that is always false is called a contradiction. If it is false for some assignments and true for others, it is referred to as contingent. The idea is that the value of the formula is contingent on the assignment of truth values to its elementary letters. Sometimes it helps if a formula can be transformed into a particular format, of course without changing its meaning. There are a number of different so-called normal forms, which are defined by rules that prescribe what the formula can look like. Before we can discuss these rules, we need a few definitions. A literal is either an elementary letter or its negation. A basic conjunction is either a literal or a conjunction of literals without repetition. That is, the same letter must not occur more than once in it. Now we can say that a formula is in disjunctive normal form, abbreviated as DNF, if and only if it is a disjunction of basic conjunctions. A formula is in full DNF if all its basic conjunctions contain the same letters. Note that the algorithm we use to construct the formula from a truth table at the beginning produces full DNFs. But how does one construct a DNF from a given formula? Well, one way would be to build the truth table and then derive the full DNF from it using the algorithm from the beginning of the lecture. However, this scales very poorly with a number of different elementary letters. So in practice, it is often preferable to transform the formula in a number of steps to produce a DNF. And this is the basic algorithm for doing it. First, all connectives that aren't and or not need to be replaced by combinations of those three. Then we use De Morgan rules to move negations inward, eliminating double negations on the way. Then we move conjunctions inward. This way we arrive at an almost DNF, a disjunction of conjunctions, except that the conjunctions may not be basic. Some contain repetitions of the same letter. If the repetitions are all either positive or all negated, we just drop all but one of them. Otherwise, if a conjunction contains a letter in both its positive and negated form, we remove the entire conjunction. Let's do this for this simple example. First, we replace the implication arrow. Then we use De Morgan's rule to move the outermost negation inside. Next, we use De Morgan again to move the negation on the right-hand term inside. We drop the double negation on the left-hand term, and then we use distribution, or multiplying out, to move the outer and operation inside. Finally, we lose the first and last term because they are conjunctions containing a letter in its inverse. The result is an equivalent term in DNF.